All right. Well, then today we're going to talk about another application of integration. Specifically, we're going to find volumes of solids of revolution. This chapter is just the coolest stuff. I mean, the areas are really cool, but volumes of revolution are also really nifty. All right. So what we're going to do is we're going to find volumes of solids that can be obtained by revolving a graph around a horizontal or a vertical axis. Now, you know, if we didn't have anything but geometric figures in the world, as far as like cylinders or boxes or cubes or spheres, things like that, we might not need this so much. But you know, in the real world, things look a little different than just your basic geometric shapes. So what we're going to take is we're going to try to find volumes of solids that look like this. Okay, and we've got a couple different methods to do so, but let's start by talking about what happens. Okay, when we did areas just now, we talked about adding up the areas of a bunch of rectangles using integration to find total area between two graphs. Well, in this next step, what we're going to talk about is taking a region and rotating that region around either a horizontal or a vertical line. But we're still going to look at what's happening to representative rectangles. So if I took one of those representative rectangles here, and I rotated that rectangle all the way around 360 degrees around, in this case, the x-axis, the shape that I would get is a solid flat disc. Okay? It's a disc whose thickness is the width of the rectangle and whose radius is nothing more than the height of the rectangle we were rotating. And so what the idea is we're going to take those infinitely many discs that we would get when we take representative rectangles and rotate them around, add their volumes up using integration, and that sum will be the volume of that solid of revolution. Now notice in this particular example, the rectangle that I am rotating around the x-axis is perpendicular to the axis of revolution. And it does have to be that way in this particular section, because if it's parallel to the axis of revolution, you don't get a disc. You get a different shape called a cylindrical shell, which we'll talk about in the next section. Okay, so the question becomes, how do you find the volume of a disc? Now remember, of a disc. Well, a disc is really just a circle, a three-dimensional circle, right? So when you find the volume of a disc, basically you have a circle that has a thickness or a height to it. So if we could figure out the area of the circular part and multiply it by the thickness, we'd have the volume of the disc. So the volume of a disc in general is pi times the radius squared times the thickness of the disc. That's just geometry, right? And so specifically in volumes of revolution, sorry, that's a little bit small there. Let me zoom in a little bit. I am going to refocus, so it may take it just a second. If you have a nice continuous function, now this one is defined to be a function of x on the interval from a to b, and the region that we're talking about rotating, say around the x-axis, is what's below the graph and above the x-axis, then this formula for finding the volume of a disk would translate to, the volume would be what we get when we add up all the little disks from A to B, and each disk, let's look at our little representative rectangle, the volume of that disk would be pi times the radius squared times the thickness of the disk is just the width of the rectangle, which in this case is dx, but the radius is just the height of the rectangles, which is nothing more than the function value or the height of the function there. So this would be the integral from A to B of pi times f of x squared times the thickness. Now this does translate similarly to functions of y, and we'll see some of those here in a minute. I don't want you to get so stuck on it being f of x, because the region could lie below the x-axis, in which case this, you need to think about it as the radius, or you need to think about this as the height of the rectangles. So it would still be top minus bottom. Okay? Questions so far? Okay, graphs, ladies and gentlemen, are really, really important in applications of definite integrals. You want to see a picture of the region that's being rotated, because it really will help you visualize, where's my radius, what's the thickness, what are we doing here? Okay, so let's look at this problem. I just got some of these from the homework set as far as volumes of revolution for discs and washers. So on this one, we want to take this region and rotate it around the x-axis. So draw your picture first, if it's not already drawn, and then draw in your representative rectangles. For the problems we're doing right now, the rectangles must be perpendicular to the axis of revolution. So if we're rotating around the x-axis, we're going to have to use vertical rectangles. That distance right there, when this rectangle rotates and forms a disk, the height of the rectangle will be the radius of the disk. So when we find the volume, we would be integrating from, since we're looking at vertical rectangles, we use the x limits on our region, which go from 0 to 1. So we'll have the integral from 0 to 1 of pi times, what's the radius? It's a vertical distance. It's just the height of this little rectangle. So top graph minus bottom graph would be the radius, or in other words, in this case, it's just the length of the function itself. And then the width of the rectangle that is being rotated, so therefore the width and the thickness of the disk would be dx, and we square the radius. This is pi r squared times the thickness. So when we simplify it on this one, it would be the integral from 0 to 1 of pi times 2 minus 2x quantity squared times the thickness. Now to integrate that one, most of the ones in this section I probably won't integrate, but like I said last time, if I hit one that I was going to go on and you want to see it integrated, just let me know. This one you could do a couple ways. You could do a u substitution with u equals 2 minus 2x, or it would also be really quick to just multiply it out and make that pi times the integral from 0 to 1 of 4 minus 8x plus 4x squared, and then just integrate term by term. Questions? All right, keep in mind, guys, on these problems, you know geometrically how to do this. You know how to find the volume of a disk. It's pi times the radius squared times the thickness. You just need to figure out from our picture what is the radius, what's the thickness, and what will be the limits of integration. The limits will always come from either the x or the y limits on your region, depending on whether you're integrating with respect to vertical rectangles or horizontal rectangles. So let's look at another one. Okay, so this one, they drew the graph for us, thank goodness. The graph over here on the right is x equals 1 over the square root of 1 plus y squared. We're going from -1 to +1, and we're rotating around the y-axis. Couple reasons that I would want to integrate with respect to y here. First of all, I don't really want to go through the process of solving this for y in terms of x. And second of all, with the disk method, our rectangles must be perpendicular to the axis of revolution. Okay? Since all of my rectangles are going from this graph on the right to the y-axis on the left, the radius in question will just be this distance right here for that representative rectangle. It is a horizontal distance, right graph minus left graph. Every distance we do is right minus left or top minus bottom. So it would be the right graph is 1 over the square root of 1 plus y squared, and the left graph is 0. This is x equals 1 over the square root of 1 plus y squared. This is x equals 0. So it's just the function itself in this case. The thickness of the little discs is the thickness of the rectangles that are being rotated. It will always be dx or dy. Specifically, when you're looking at horizontal rectangles, it's dy, and when you're looking at vertical rectangles, it's dx. Since we're doing horizontal, it will be dy. Is everybody okay still so far? All right, so our volume will be the integral from -1 to +1, because those are the y limits on our region. Smallest limit on the bottom, largest limit on the top. Pi times the radius squared times the thickness. Now I want to go ahead and integrate this one. So I would factor my pi out front, and we'll have the integral from -1 to 1 of, when I square that fraction, I will have 1 over 1 plus y squared dy. Who can tell me what the integral of 1 over 1 plus y squared dy is? Remember, it's special. It is. Which one? Go with another one. Starts with a T. Yes. So this would be arctangent or inverse tangent of y from -1 to 1. Excellent. And I know that you've all made your flashcards from those 19 things you know how to integrate, and you're memorizing those, right? Excellent. Okay, so we will have pi times the arctangent of 1 minus the arctangent of -1. So that's pi times the arctangent of 1. Remember, that is an angle between -pi/2 and pi/2 whose tangent value is 1. So that's a pi/4 and the arctangent of -1 is negative pi over 4. So we have 2 pi over 4, which is pi over 2 times pi, which is pi squared over 2 cubic units in this case. That U is just to represent, I don't know if this was meters, centimeters, millimeters, whatever, but whatever it would be cubic units. Any questions about that problem? Okay, I want you to try one, okay? So I'm going to look at, and I'll go ahead and draw the graph here, though I know you could get it there pretty quickly. Let's see, our region is bounded by y equals e to the x. Y equals 0, which is the x-axis, x equals 0, and x equals 2. So this is the region in question, and we're rotating it around the x-axis. So on your paper, I want you to identify what is the thickness of the rectangles. Is it dx or dy? What is the radius? And write down an integral for the volume. Okay, so first things first, and we'll give you a hint on this one, and then I'll let you set up the next one completely by yourself. Okay, what kind of rectangle must I be integrating if I'm going around the x-axis? Is it vertical or horizontal? It's got to be vertical. Excellent. It must be perpendicular to the axis of revolution. So fill in those little bits right there, and then we'll compare. Would you hush? All right. Anybody willing to tell me what they got for the thickness? dx or dy? Perfect. It will always be dx if you are using vertical rectangles. The radius is the length of these little rectangles that we're rotating. Top graph minus bottom graph ends up being what in this case? Good. E to the x minus 0, which just simplifies to e to the x. Perfect. So our volume will be what we get when we integrate from 0 to 2 pi r squared times the thickness. Now remember, when you're integrating this, that simplifies as the integral from 0 to 2 of pi times, when you take a power to a power, you get e to the 2x in this case, because power to a power, you multiply the exponents. And remember, that one would just be pi times 1/2 e to the 2x from 0 to 2. Because if you have the integral of e to a constant times x dx, it's just 1 over the constant e to the kx plus c if you have an indefinite integral. We had a definite integral, which is why I didn't have the plus c. Everybody good? Okay, so I want you to try one more, just a setup. Now this one's a little bit too small there. Okay, here's what I don't want you to get bogged down on. I don't want you to go, oh gosh, I've got to go buy a graphing calculator because I have to graph this perfectly or anything like that. In fact, I would rather you didn't use a graphing calculator. What we want to do, we just need a general sense of where the graph is. It doesn't have to be a perfect graph by any means on these. We just need to know, is it above the x-axis? Is it below the x-axis? Where is it? Because in this case, we're going around the x-axis, even though that print is so tiny you may not be able to see it. Okay, so when I draw this graph, I don't really care exactly, what the shape of it is or anything like that. I just need to know about where it is. So, couple things I want to notice. The numerator of this fraction is always positive 7. And when you take the denominator and look at it, the fourth root of a positive number is always positive. Square roots, fourth roots, sixth roots, even roots are always non-negative answers. So this graph will always be greater than 0. It can't actually equal 0 because for that to happen, the numerator would have to be 0. So this graph has to lie above the x-axis. Specifically, when x equals 0, we're at when x equals 0, we're at 7 over the fourth root of 25. Do I know exactly what that number is? No, but I know it's up here somewhere. Okay. When I plug in 5 halves, I'm at 7 over the fourth root of 25 halves. We had 7 over the fourth root of 25 and 7 over the fourth root of 25 halves. So the denominator on that second fraction is smaller, and so my answer would be a little bigger. It's doing something in there. It's not a straight line. I don't really have to know exactly what it looks like, but I need to know where it is. So I just plotted a couple points and I'm going to connect the dots. Now, I am not saying that this is what that graph looks like exactly. I just needed a general sense of where the region lies. Okay, so if this is this graph, very, very roughly, I want you to set up an integral to find the volume when this graph is revolved around the x-axis. When you get to a point where you've got it set up, if somebody would just type in the chat that you're ready to go, I want to give everybody a chance to at least start it before I jump in. All right, so let's look together. Since I'm going around a horizontal axis, I'm looking at vertical rectangles, right? I need a thickness and a radius. The thickness is this distance, that's going to be a dx. The radius is this height, so that's a top minus bottom. The thickness is dx here, the radius top graph minus bottom graph would be 7 over the 4th root of 25 minus x squared minus 0, or just 7 over that 4th root. So when we go to set up the volume, did you get that it would be the integral from 0 to 5 halves of pi times the radius squared times the thickness. Yay! Excellent. Now, just be aware, this one is not as terrible an integral as you might think at first. If you square that, when you square a 4th root, you get a square root. So this would be the integral from 0 to 5 halves. I'm going to factor the pi out front. And that would be 49 over the square root of 25 minus x squared dx. So that would be 49 pi times the integral from 0 to 5 halves of 1 over the square root of 25 minus x squared dx. Running out of room here. Okay, so that would end up being, whose derivative is a squared minus x squared underneath the square root in the bottom? That's an arc what? Yes, excellent. So that would be arc sine of u over a. So that would be 49 pi times the arc sine, or you could write it as the sine inverse if you prefer, but it's the arc sine of x over 5 in this case. I didn't actually switch it to a u because it was just x squared, so I didn't have to go that far. But we'd have the arc sine of x over 5 from 0 to 5 halves. And so we would end up with 49 pi times the arc sine of 5 over 2 over 5 is 1/2 minus the arc sine of 0. And the arc sine of 0 is 0. The arc sine of 1/2 is an angle between negative pi over 2 and pi over 2, whose sine value is 1/2, which would be pi over 6. It looks like we would end up with 49 pi squared over 6 cubic units. Is everybody all right here? Okay. Oh, go ahead. You mean like going from here to here? You have to know the definitions of the inverse trig functions, and you've probably not dealt with them a huge amount. But when you take the arc sine of a number, so I'm just going to say the arc sine of x, that by definition is an angle or number between negative pi over 2 and pi over 2. I'm going to write it in interval notation. So it's a number in the interval from negative pi over 2 and pi over 2 whose sine value is x. So written it, let me write it in like equation form. So if we have y equals the arc sine of x, for example, that means that the sine of y is equal to x. So the reason I was able to go from here to here is they gave me a nice angle, and I know my unit circle. Sine value is a half when your reference angle is pi over 6 from the unit circle. And so that's how I did that. If you need to, you can plug it into your calculator, and a lot of times you'll actually have to, because it might not be some nice unit circle function. And so if I was going to plug it into my calculator, sorry, but this is the only one that I have sitting here. Let me get that cleared out and see if I can. I'm going to turn off the light just to get rid of the glare for maybe some of the glare. Well, maybe not. Sorry, it has to refocus every time I do something weird on it, but okay. Okay, so first thing I would do is make sure my mode was actually in degrees, and mine is. And that's just because I don't typically recognize the values when it's in radians. So if you take the arc tangent or the inverse tangent of, I'm so sorry, that is not terribly visible. It doesn't really like that. But I'm going to take the inverse tangent of 1/2 or 0.5. What it will come up and tell you, not inverse tangent, inverse sine, sorry. I was going to try to move it to see if I could get it to show up a little better. But I've got an inverse sine of 0.5. It's going to tell me the answer is 30 degrees. And then, since our answers, that just made it worse. Once you get that it's 30 degrees, switch that to radians, and that's where you can get pi over 6. But when you're talking about inverse trig functions, what you're really doing is you're looking for an angle in their given ranges where the sine or cosine or tangent of that angle is the number inside the inverse function. So if you had, for example, say the arc cosine of the square root of 2 over 2, you would be looking for an angle in the interval from 0 to pi, because that's where arc cosine is defined, whose cosine value is square root of 2 over 2. What size angle has a cosine value of square root of 2 over 2, as far as what size reference angle? It would be, exactly. So that would be pi over 4. But if it had been the arc cosine, for example, of negative square root of 2, you would have said it's 3 pi over 4. Because we have to put it in the correct quadrant. Cosine between 0 and pi, cosine is negative in the second quadrant, not the first. And we would still need a reference angle of pi over 4. So in the second quadrant, that corresponds to 3 pi over 4, which is probably more than you wanted to talk about inverse trig functions on there. But there you go. All right, I want you guys